first thing you're going to want to do, set your side equal to 0. Okay? So you set your side equal to 0. You have 3x to the 4th plus 3x cubed minus 6x squared minus 6x is 0. Now you can do one of two things right off the bat here. You can take the GCF out right away, which was 3x, or since it's 4 terms, you can factor it via grouping right here. Either method's going to work out just fine. Me, I saw this, and I'm like, oh, I'm just going to factor it via grouping because it'd be a little bit quicker. So I just went and grouped them. I took out the 3x cubed, and I get x plus 1. I took out the negative 6x, and I get an x plus 1. Okay? Now I have the 3x cubed minus the 6x, and then I have the x plus 1. This next setup is when I would take out the 3x. You're either going to take it out at the beginning, or take it out in the middle, or take it out at the end. Eventually, it's going to have to get out anyway. So if I take the 3x out here, now I have x squared minus 2, and then x plus 1 equaling 0. From here, you can't factor the x squared minus 2 any further, but you can still solve for its zeros. Okay? So this was a 4th degree polynomial, which meant how many zeros should we have had? Should have had 4 of them. In this case, the first 0 is 0. The next one is plus or minus root 2, very good. And the last one is at boom shakalaka. I haven't had a good boom shakalaka in a long time.
71.
I was going to do 83 first, but yeah, look at that. What's that? What? Yeah, this is a pretty straightforward one there. 83, same idea. There's a trick in this one that you may or may not have caught. I think before we left class yesterday, I said, hey, you always want your highest degree polynomial to be positive. So I would have moved that one over, and I've gotten 2x to the 6 plus 16 is 0. I'm just flip-flopping the side that 0's on. That doesn't make a difference there. Okay? All right. So then you have GCF, which would have been 2. Then you have x to the 6th plus 8. Now, at this point, you probably started going, well, that's 2 values, but I got to figure out, is that a sum or a sum of cubes? I know 8's a cube root, but what is x to the 6th? How do I make that into a cube root?
Take out x cubed.
What is it? Or, you can't take out x squared, x cubed, but what, I think you were just x squared cubed. All right? Remember, think of it this way. When you get something to the 6th power, all right, if you have something to the 6th power, that is x, 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 right? Isn't it also right? And isn't there 3 of those? X squared cubed.
Oh, that makes sense.
Right. What happens here, there's a couple little tricky exponent rules that I'll throw in here from time to time. This is the only time you're really going to see it. I try to stay away from those yet. We'll get more to the funky, crazy exponent rules when we get to, I think, rational exponents. That's when we really get involved with them. I just thought it'd be, because we talked about the x to the 5th being 5 x's. I thought this one you might have caught, but if you didn't, it's not the end of the world. This was x squared cubed, all right, plus 2 cubed. So if I'm going to find my zeros now, this 2 has no bearing upon the problem anymore. Are we okay with that? So now this is just a sum of cubes. So this pattern would be a plus b, x squared plus b, and then the last part would have been a squared. Well, if I square x squared, that means there's 2 sets of them. So how many exponents do I have now? X to the 4. Plus, here's also a dead giveaway. You need to get x to the 6th, and if you start multiplying in, what's x squared times x to the 4th? It's going to be x to the... Yeah. And then I subtract, multiplying the 2 together, and then then I square the last term. Okay. The only zeros that you could get out of this one would have been plus or minus I root 2 here. That's the only zeros you could get. You don't know how to do this yet. We'll learn that next week, okay? So, and I knew that was going to happen. I just wanted to see if you guys could figure out this. That was the only reason I threw that one on there. Okay. Normally, I wouldn't do something like that. Okay. 71.
Yeah.
Same thing. Yeah, it's a sum. This is a sum of cubes. So, what's the cube root of x cubed? X. What's the cube root of 27? 3. So you just follow the pattern with x's and 3's. So this would be x plus 3, first term squared, minus multiply the two together, last term squared. The only real zero you're going to get is at -3. The other one you have to use quadratic formula. Okay? If you want to complete the square, go for it, but it just takes too long. Quadratic formula is real quick. Opposite of b plus or minus the square root. B squared is 9. Please, 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 you guys are still screwing up the b squared when it's a negative. Remember, when it's a negative b value, when you square it, it's going to be positive. Please stop messing that up. -4 times 1 times that. I think we did this one yesterday. Your discriminant, I forgot what it was called, would be -27, and this was all over 2. So your two roots were plus or minus 3. This was -27, so that was 3i root 3 all over 2. So here's your 3 solutions. Okay. A lot of times when you see the difference of squares, difference of cubes, they try to keep the cube roots manageable. So you're going to see a lot of 27s. So you'll see a lot of 3 squared, things like that. You'll probably see that -27 a lot is underneath the square root symbol. It's the same thing with like -12. I think we've done that one a few times as well. Okay. Sure, why not?
Yeah. How about we give it for I want to hear the Darth Vader music.
All right, we'll play Darth Vader music, 'cause I haven't had that on for a while. There we go. I don't. Why are you yelling?
Raylan yelled at Trinity first.
Raylan, don't make me touch the sign.
Oh, it's my impact comment. Yeah.
I was there just in case. Yeah, what's with the 2? 5 minutes. Let's go. Let's finish this by 8. So where does this get us to go? What's going to happen here is that we're going to start talking about the end behavior via the graphs. Okay. As of right now, you guys know how to find zeros. You know how to plot zeros. We just don't know what these graphs look like. Well, one of the ways that we start to look at these graphs is by looking at what are called the tails. And what I mean by that is, remember, don't write all this stuff through here. One of the things that we start to look at when we start graphing this stuff is that we're going to start looking at what are called the tails of polynomials. And once we talked about polynomials earlier, we said that polynomials were basically anything written in the format where it's highest degree on down to lowest degree. All this stands for is some constant in front of a variable to the nth degree. Like yesterday you had x to the fourth. And it went descending order all the way down to a constant, plus 2. Okay? That's what a polynomial was. It wasn't anything fancy, it wasn't anything crazy. But what these nth degree things allow us to do is, obviously we talked about this one. Whatever your nth degree was, it told us the possible zeros. We looked at that yesterday. We figured out that when we had that 5th degree polynomial, we had up to and including 5 possible zeros. Sometimes they were repeated zeros. When zeros were repeated, what do we call them to have? Multiplicity. Good. So you had 5 possible zeros if it was a 5th degree. You knew that, well, we don't know this yet, but what'll happen is you're going to get up to n minus 1 changes in directions in the graphs. So if it's a 5th degree polynomial, the graph can change direction 4 times. Does it mean it's going to change 4 times? No, it's possible changes in direction. So I probably should write that up there. We'll have possible changes in directions. And then the other bit there was, the one that we did know, was that there was n, if it was a 5th degree polynomial, it could have up to how many terms in the sequence? 6. Okay. So remember, you had 5th degree, 4th, 3rd, squared, x, plus a constant. That's what that means for possible terms in the sequence. Okay. So the reason why I say that is, as we get to next week, one of the things that we'll learn about and explore through is that there are going to be placeholders. Okay. If you go back to, I think this was one in homework you got. There's going to be placeholders, and I wanted to show that with this. What's the degree of that polynomial? 4th degree, right? How many possible zeros should there be? 4. It should have 4 total zeros. How many changes in direction could this graph have? You have 3 changes in direction. How many terms in the sequence should there be in this polynomial? 5. Why don't we see all 5? Because what? We have zeros. Very good. What this is, basically what this is getting at is, eventually we're going to do this. 2x to the 4th plus 0x cubed minus 26x squared plus 0x plus 72. And just like you said, those zeros will become what we call placeholders. Okay? It's not so much super important yet today, but with all this other stuff happening with the graphs, it's not a bad idea just to kind of give you guys a heads up of what you're going to start to see more of. Okay, that's why we keep talking about our n values. So what I want to do though is I want to look at, excuse me, go back to here. I want to look at our graphing calculator. So take out your calculators real fast, and I have this little worksheet kind of built in as far as what certain values of things I want you guys to mess around with. If your calculator is all still sorts of messed up from quadratics, go ahead and do a hard reset real fast. Do you guys remember how to do that? No. Do a second 712, and do a second plus 722. That'll reset everything in the calculator, so you don't have to worry about if your windows are all messed up, all that kind of fun stuff. Staples. I'll reset it and clean it, so that way when we're looking at our graphs, it won't be so bad. Okay. So what I want you to do here is, remember, it says f, yes sir, it says f of x. Remember, f of x is synonymous with y equals. F of x is synonymous with y equals. What does synonymous mean? The same. You guys. The thesaurus. Use the thesaurus, the source. Don't look at me with those mean looks of disgust. Yeah, you do. Very upset. Anyway, so what I want you to do is in your calculator, I think I started with what? X squared, x to the third, x fourth, x to the fifth, x to the sixth. Do you guys know how to do exponents?
Yes, carrots.
Okay. Carrots. So x to the third. The caret button is one above the division symbol. Anytime you use the caret button, one of the things you'll notice is that, see how my cursor stays up there? Obviously, it's not going to be that big of a deal for right now, but eventually, if you have to add more things to it, you got to make sure you hit the right arrow to get it down to the regular level. And just keep on going through. Then we have what? X to the fourth, x to the fifth, and x to the sixth. Okay. Now, pick graph. I bet you my window's all jacked up here. Change one.
Whoa. Rainbow. Flip it upside down.
What's happening?
A lot of graphs. A lot of lines, a lot of graphs.
A lot of lines, a lot of graphs. Yes, you're right. Doing a lot of this. Yes, this. Now, what did you notice between the ones that had, yes, ma'am? It has different tails. So what I mean by tails, the tails of these polynomials are what's happening at the very ends. What's happening when x is really, really small? What's happening when x is really, really big? Okay. So as you go through this, the first graph that showed up there was x squared, right? An x squared graph was just that, correct? It touched the at 0, right? Yeah, I know what you're talking. Yeah. I'm not worrying about the middle. I'm looking at the ends. So the x squared, the x to the fourth, that was x to the fourth, wasn't it? And then x to the sixth was a little bit quicker. So x squared, x to the fourth, x to the sixth. What do all three of those have in common? They all have an even exponent, don't they? Okay. They all have an even exponent. All right. Now, in the other one, that was x cubed, right? That was x to the fifth. And x to the seventh. What do all those have in common? They're all odd. They're all odd exponents. Okay. All right. Now, go back to your calculator. Do you guys know how to insert?
Yes.
Insert, because the next round of these things here says to insert negatives. There's a button that says insert. So once your cursor is blinking on the X, second insert negative. Second insert, and the negative button is down at the bottom. Oh, real fast on that last one here, one that I forgot to put in there. Just do x, y equals x.
Why does it, yeah, because it's graph all.
Yeah, it's gonna graph all of them before he goes back. So
Wait, negative x?
I just did regular x. I thought. Yep.
I have a proposition.
What's that?
The higher the number of exponents, the closer it gets to the y.
Yes, I will give you that. When your a value is what though?
1.
Correct. Okay. What's happening there is that if you think about it, if you're substituting values of x, what's 1 to any exponent? 1. What's 2 squared?
4.
What's 2 cubed? What's 2 to the 4th? 16. What's 2 to the 5th? 32. So each one of those x values, when it's at 2, is increasing each time as it raises up the exponent. So you're right, that the curve becomes tighter, I guess, if you want to think of it, as it goes in through that. But what happened with the a values here? They're all negative. What did it do to all the graphs? It flipped upside down. So,
Bruh.
I thought it was, I was so hoping it was yours. It would have been great. So, now, you guys actually know a little bit about this. What do you know about this?
It's not that. It's not
Okay, well, is it up like a cup or down like a frown?
down like a frown. Because the a value is negative.
So the a value is negative. The a value is negative, so we said it was down like a frown. What are the tails doing there?
They're being sad. They're going to like.
They're pointing downward, aren't they?
Yeah.
Now, did that change when this was y equals?
Yeah.
What were the tails doing on that one?
They're going up like.
Why were they up like a cup?
Because the a value is positive.
A value is positive. Now, what do both of these functions have in common?
They're both.
They're squared. Very good. They're both squared. Okay. So we know a little bit about quadratics. All right. What's that?
So,
Very good. Slope-intercept function. Okay. So let's see here. If I did this, oops. The slope is negative 2/3. So if you were to graph that, where do you start? Then what's your first step? Go down 2 and then, so you would go wherever your negative 4 was, you would go down 2 over 3. So what way are your tails going?
Going down.
They're going this way, right? Okay. What's the exponent for linear?
1.
It's first degree. Is 1 even or odd?
Odd.
Okay.
That's very
I get it. Go back and look at the little sketch you made. What did the sketch of x cubed look like? Do you remember?
It's going.
So, all right, what I want you guys to think of is, as you're looking at the graph, what's it doing?
It's going.
So it's going down, up?
No, it's on the other. No, it's on the other side. Oh.
Oh, I'm sorry. Yeah, it's moving.
Yes.
Yep.
Okay. Now, here's the thing. Does that change if it's that?
31. No. Yeah. No, it's not closer.
But the tails themselves are still pointing in the same direction, aren't they?
Yeah.
So I don't know what all this is doing in the middle here. I know if I have x to the 31st power, what's the y-intercept have to be? It's got to be 0 because there's no constant there, right? So I know it's got to go through 0. But no matter what, my ends of my graph are pointing down, and up. Okay. What does it do now? It goes the other way. So no matter what, I mean, this always tends to work. What if it was this? Oh, they're down, down, aren't they? Now, what I'm saying is, what we're looking at here for via like down, down, in as x. Do you guys know what this symbol is?
Infinity.
Infinity. What does that mean?
Sideways.
What is the concept of infinity mean? Yes, ma'am. Never ends. It's getting larger and larger and larger in one direction. Okay. What is that?
Smaller.
Negative infinity. So if you think about it in terms of a number line, x gets incrementally smaller going that way, bigger going that way, right? So x's are your input to a graph. Your y's are your output, okay? So as x gets larger, the function of x, or f of x, approaches something. Now, let's come up with an idea. What's your idea? What are the tails doing if A is even, if A is positive and x is even? Up, up. Okay? That means your tails look like that. If A is positive, exponent is even, your tails are up.
I like Is it like this? Like, football?
Now what are they doing?
Down.
They're down, down, right? Okay. Now, the reason why I wanted to show this here, this stuff, textbooks write it very long-winded. What happens is, as x approaches infinity, f of x, if I'm going to use it for this one, for this example, as x gets larger and larger and larger, what is f of x getting? Larger and larger and larger. It's also approaching positive infinity. As x gets smaller and smaller and smaller, what is it doing when it's a is positive, x is even? It's also getting larger and larger because it's up. Okay? I've always thought of it as easier to see by showing the tails. Knowing what you're doing dance-wise. Okay? The way I look at it, I know it's stupid, but the way I look at it is I'm always thinking of it as I'm going from left to right of my graph. If this is A is negative, your exponent is even, it's down, down. Always. Okay? Now, same idea. Positive A, x to an odd. What are your tails doing? Think of it as reading from left to right. Left to right, what is it doing? The tail on the left is doing what?
Up, down.
Down. The tail on the right is?
Oh, yeah. Oh, yeah, this is how I remember stuff.
What? I was talking to you.
There's always one. Okay? So the idea here is that your tails will allow you to plot and graph. Same idea here. Negative A, x to odd. Now what are they doing? Up, down. Okay. Up, down. Okay. Did you seriously just accidentally throw it in and land in that spot? That's pretty freaking awesome, just out of the rest of it. Okay? Now, homework last night. We did this problem last night. What are the tails doing?
Oh, going up.
They're both up, right? They're both up. Do you remember what the zeros were for that problem? So if we had to factor this one, what's the first thing you would do? Take out a 2, right? So you take out your 2. I know our tails of the graph are going to look like that. What times what's 36 you add together to get negative 13? Negative 9, negative 4, good. So we have x squared minus 9, x squared minus 4. Now, does that value of 2 have any bearing upon the problem whatsoever? What are your zeros? Okay. Now, in the graph, fourth degree polynomial can have how many possible zeros? 4.
4.
How many changes of direction can it have? 3. What are the tails doing? Up. So I know that somewhere over here it's going up, somewhere over here it's going up. I know one other point on this graph.
0, 0.
Yeah.
Wait, no. 36.
36. Why is it going to be at 36?
Because that's the y-intercept.
So I know that no matter what, it's got to cross through there, doesn't it? Okay, so now it passes through there, but somewhere it's got to change direction to go back up, doesn't it?
Yeah.
Okay? It's got to keep going to get to here, right? It's got to change it down, doesn't it? It's got to come back up, doesn't it? 1, 2, 3 changes of direction. Tails are up.
What? Oh my gosh.
Now this, in this case, this is rather clean because what kind of zeros do we have here? Real. We have real zeros here. When you have real zeros, it's pretty clean to set this stuff up. When you get imaginary stuff, we have to learn how to do some other things. Okay? We got to learn to do a few other things. But the idea is, we know how to do this. We know that we can fall back on up like a cup, down like a frown, because those are even, right? We've been doing those forever. You can also fall back on linear. If your slope is positive, you're going down up, aren't you? If your slope is negative, you're up down. Isn't 1 an odd number? Works the same. So in essence, you've actually known how to do this forever. You just didn't realize it. Okay? This is this extra pieces that we're learning about. Okay? So if I look at this, falling back to a quadratic, what are your tails doing? They're up, right? Tails are up, okay? So if my tails are up, I factor that. What times what is 9 I add together to get negative 6?
Negative 3, negative 3, negative 3.
Negative 3, negative 3, okay, so. Okay, what's my 0? 3. And what? 3. So 3 has multiplicity, doesn't it?
Yeah.
How many times is it 2? Well, you're right. I'm sorry, you got ahead of me on that one. What happens at 3 for the graph? Changes direction, doesn't it? Multiplicity is even, isn't it? Because it's there twice. Okay. So we know that the graph has to hit 3, and it's got to hit 9, right? It's got to be up like a cup. One change of direction, where did it change direction? It changed direction at the 0 because the multiplicity was even. Wow.
Because you can change direction of line because it's to the second degree.
Correct.
So he's saying that like because you have a 2
Yep.
and then 2 degrees,
When your multiplicity, if you have the repeated 0, it changes direction at the 0. Obviously, there's a lot more going on that we'll get into. What I have for you tonight is something pretty quick. It's real simple factoring problems, and what I want you guys to do is spectrum, plot your zeros, and graph the tails, and see if you can get in general shape. Try not to use your calculator. Get your finger just a little damp and it works. Alright? So as you're going through these, obviously there's a lot more we're still going to explore through this. Next one. But for the most part, you'll start to recognize these patterns as they go. Alright? I made sure that I gave you guys things with reals. Maybe there's a fraction or so. But it shouldn't be all that difficult to make that jump and see what this is going to look like. Okay? Woo-hoo. Remember, always fall back on the tails of quadratics or linear to help you through. It's a lot for Friday. We'll probably want to do those on Monday. What I wanted to do, guys, I'm going to set up the video stuff probably for Monday. I wanted to make sure that I got into this stuff for today. Plus, that way I had time to compile everything into one file, and I could play through all of them rather quickly. I just wanted to make sure I had time to do that.
Do you want the FPLA? I think I got through.
Yeah, go for it. Yeah, absolutely. Yeah. Should have said something earlier. I would have said go.
Well, I didn't realize so damn.
Oh, well, I hope it's still there.
Wait, are we gonna watch the
Picky.